Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a new concept regarding the force exerted by a jet of water on a series of vents. So previously we have seen many conditions regarding the force exerted by the jet of water. Like series of vents here we are considering. Previously we have seen the vane is nothing but actually this is also called plate. This is also called plate, or you can also call it as a bucket also. So up to now we have seen different types of categories. You can see like different types of plate. Either the plate is in moving condition or the plate is in stationary condition. We have seen initially we have seen the stationary condition. After that we have seen the moving condition of plate, and even the plates also taken different shapes of plates. Like some plates are vertical, you can say, or flat, or you can say this is vertical condition of plate towards the jet of water, or some plates are like inclined, you can say. Some plates are kept in inclined position, and some plates are either flat, or second one we can consider this is curved. So in the flat plate, it is vertical or inclined, and another one condition is curved plate. So these are the shapes of plate, and these are the direction, or you can say the movement of the impact of jets towards the plate. That means in the moving condition or stationary condition. Okay, so these things already we have discussed. But if you observed that everywhere we used to discuss only single plates. Okay, everywhere if you see, we have taken a single moving plate. See, moving condition means only moving, like some changes of distance will be there. Stationary means that is fixed. So here we are going to discuss series of vanes. So now we can consider moving of vanes means till now we have taken suppose one vertical or one flat vertical plate we have taken. So single one taken. Similarly, if it is a curved plate, we have taken a single curved plate. Okay, but if you see really in practically, single plate impact of jet is not at all possible. Like what will be the practical application of the single plate? Okay, so actually if you consider practically, okay, we need to consider number of plates or number of vanes which is mounted on a wheel, okay, or that is called also runner. So the single plate what we have studied, these are the studies are done theoretically. These are the studies are done theoretically. Okay, but here if you see practically, it is not at all feasible. Single plate studying is not at all possible. So we need to consider number of plates or number of vanes or series of vanes. We can see some series of vanes or series of plates. So here we have considered a wheel where number of plates or vanes are mounted on equal distance. You can see equal distance, it is mounted on the wheel, or this is also called as a runner also used to call this is. Okay, so the number of blades are mounted on the wheel so that it can rotate easily. Now here we have taken a jet of water, or a pipe is there, normal pipe is there. From this pipe, this is the nozzle connection, and from this the jet is coming out. That means the fluid which is coming out from this, that we are calling as the impact of jets. So here if you see impact of jets on the one plate, this is one plate. Okay, after impacting here, this jet is going to move here, this plate is going to move. Okay, so it is moving with a velocity of u, and once it will go, another second one will come in this position. Now second one will go again, third one will be go in this position. So if you see, all by this rotation, because as I told you, this all the plates are mounted on the wheel, or that is also called as the runner. And this part you can see, this part actually you can say this is the shaft part. Okay, at the middle of this wheel, the shaft will be connected to this one. So basically we have seen this kind of things in the turbine case. We'll study in the future turbine case, there we can understand. So, and this will start at rotating in this direction. So the direction is given here, and we need to find out the force exerted by the jet of water on the series of vanes. Now previously what, only single plate was there or single vane was there. Now once it started display moving, then it will come like this, suppose. Now here it is different. Once it's striking here, now how it is striking? That is striking tangentially at this point. Okay, once it will go out, again second vein will come, third vein will come, fourth vein will come. So all the vein is going to be struck by this jet. Okay, so that's why here the case is like, you know, mass of fluid, that will be different here. So anyway, first of all, I'll tell you some important parameters here. So one is V. So V is nothing but velocity of jet. So this is very, very simple. First one is velocity of jet. Second one, small u we can consider. This is actually velocity of vein. This is velocity of vein or plate, I can say. Vein or plate, both are same. Similarly, next one. Now we can see the velocity of this fluid which is coming out from here. It will have a diameter, okay, or having the area of cross section. So to find out this area of cross section, we should know the diameter of the jet. So we need to consider small d, which will give the diameter of jet, and from here we can find out the area, cross sectional area of the jet, which is nothing but pi by 4 d square. Okay, these are the terminology we need to consider. Now in this case, actually the mass of water which is coming out from the nozzle per second, this is the nozzle, as I told you, the mass of water which is coming out from this nozzle, okay, that will be always in contact with this, any of the plate, either this plate, this plate, this plate, this plate, any of the plate will be contact. Okay, so because here number of plates are here available, so the mass of water we need to find out. Actually, first of all, we need to find out the mass of water per second, striking the veins, per second striking the series of veins, you can say, striking the series of veins. So previously we have seen, okay, previously equation what we got, I'll write here actually, that is actually rho a v r1, okay, rho a v r1, that is relative velocity actually. But here, though relative velocity need to consider, not for this mass of water per striking. So this one actually we can write, how you can write, this is rho a v, rho a v. So how we got rho a v? Also I told you a number of times previously, mass of water per second, mass of water per second. So this one we can write mass per time, and here mass place I can write, as I know that rho equal to mass by volume. So what I can say, mass equal to rho into volume. So in the same thing I'll do it here, rho into volume by time. So this volume by time, I can say this is a quantity of flow or nothing but discharge. So this one we can write discharge Q. So Q equal to, also we can write rho AV. So Q plus I can write AV. So this is nothing but area into velocity. So in this way I can write this equation. Now here we need to keep in mind that we should not consider the relative velocity for this condition, but when we need to consider the jet striking the plate, when we need to consider the jet strikes the plate, at which velocity it is, at that time we need to consider the relative velocity. Okay, so the next one we can write, the jet strikes the vein, the jet strikes the plate or vein, we can write anything, vein with a velocity, with which velocity, with a velocity that is nothing but relative velocity, that is nothing but relative velocity. So relative velocity equal to what? Already we have seen previously. What is the relative velocity? Two vehicles are moving in the same direction. Suppose this is the velocity of VA and this is the velocity of VB, and this is suppose moving with 50 meter per second and this is suppose moving with 10 meter per second. Then we need to find out the relative velocity for any one particular vehicle. Okay, and which vehicle is having more velocity, for that we can consider. So relative velocity for VA with respect to, we need to write like this, with respect to VB. So relative velocity of VA with respect to VB. how much, like that we need to find out. So similarly here also we need to find out the relative velocity of the jet with respect to the vane. So here what we can calculate, we can calculate like v minus u. Now here v we need to consider absolute velocity, and this is velocity of the vane, this one. Okay, so in this way we need to consider this. This is our relative velocity. Now as per the definition, what we need to calculate, we know that the force exerted by the jet, so we need to find out the force exerted by the jet in the direction of motion. That means here in the direction of motion in the sense in this direction, that is x direction. So I am writing fx as per the Newton's law of second law of motion. We can write fx equal to mass into acceleration, and the same thing again I can write here, mass value already I got previously, and acceleration place I can write this is dv by dt. Okay, this is mass I didn't get, mass of water per second I got. So here also we can convert into, like if I write this one acceleration we can write change in velocity with respect to change in time. And similarly again we can write the same sentence, this is mass per second or mass per time, change in time we can write time, this one. And here change in velocity, so change in velocity nothing but initial velocity how much, and this is final velocity how much. So here I am taking initial velocity first, final velocity, that means v1 minus v2. If suppose v1 here, then what about the v2? V2 final velocity. So initial velocity we need to consider, that is relative velocity. As I told you, we need to consider the jet strikes the vane with a velocity that is called relative velocity. Okay, that we need to consider. And what about the v2? V2 is the final velocity. So this one I can write, this is initial velocity, and this one is actually final velocity. Okay, these two are there. Now after striking, see, before striking, this is after striking, you can say. So after striking, the jet moves, you can see the jet moves tangential to the plate. You can see the jet's moving like striking here at the tangential to the plate. So the velocity component, what will be there in the direction of motion? See, in the direction of motion, what is the velocity component? If it is inclined is there, then we can calculate some kind of velocity component. If suppose v is there with an incline of theta, then we can write something. Okay, v1 cos the sine theta we can write in this horizontal direction or in vertical direction. Okay, but here if you see in the tangential direction striking, then the vane is moving. So the velocity component in the direction of motion in this direction is nothing but 0. Okay, no velocity will be there in this. So the final velocity is this one. So we can write fx equal to, again we can write, this is rho av, this one mass per time, what we got here, this is rho av, and here we'll write this is v minus u minus 0, initial velocity minus final velocity. And finally we can write this is rho av, and here it is bracket start, we can write v minus u. So this is our equation. So we can write in this way, or else we can write as per the Newton's second law of motion, we can write in this way. Now once you can see, once you calculate the fx here, if it is a stationary condition, no need to find out the work done. But when you see there is a movement is there, there is a distance covered by this plate, movement is there, then we need to identify the work done. So work done, we need to write work done by the jet, work done by the jet on the series of vanes, on the series of vanes per second. Now yeah, one more things I forgot to tell you. See here actually what I have written, v1 minus v2, this is v1 minus v2, correct? So this one if I write here, this is again I can write this is rho va, and this is v1 minus v2, correct? This one actually, why I have written v1 first, because we are going to calculate the impact of jet on the plate, impact of jet on the plate. So impact of jet is nothing but here v1, okay, like initial velocity, and final velocity is what is the direction of this or the movement of this in the, and when we can consider v2 minus v1, now when the point will be given the impact of plate on the fluid, on the jet, then we need to calculate v2 minus v1 in that time. Yeah, similarly work done by the jet on the series of vanes per second. This is equal to, we can write this is force in the direction of motion and the distance per second. This is actually distance per second in the direction of force. So we can write this is nothing but Fx into u, and already we got the value of Fx, rho a v bracket start v minus u bracket close and into u. So this is the work done by the jet on the series of vanes per second. So this is per second. Only work done means no need to consider the distance per second. Why I have considered distance per second? If see, simple. If only work done is there, I can calculate force into distance. Okay. So distance is not given. So what we'll consider here, if I consider distance per second, and this one I can write velocity, because velocity equal to or the distance traveled with respect to time. So we can write this. So this is our work done. Okay. And this is our force Fx. This is the force exerted by the jet, and this is the work done by the jet. Now similarly, we can find out the efficiency. You can calculate also power, also you can calculate efficiency. Efficiency equal to what? We know that output by input. So what is the output actually? Output is nothing but what we have calculated. That means the work done per second. Work done per second divided by what is the input is there? Input is nothing but the kinetic energy per second, which was given here at this point. What is the kinetic energy of the fluid? This is kinetic energy per second. So here we can write what is the work done per second. Just now we have calculated this. So we can write this is rho a v bracket start b minus u into small u divided by, this is half mv square, half m v1 square. So we can write this is, again we can write this is rho a v b minus u into u divided by, this is half rho a, and here also we can write this is v. So here v1 or v2 nothing is there, we can only consider v. So you can write half mv square, this is m, and v square, so vq. So we can write finally, let me cancel this rho a, and here v will be cancelled, so only square will be there. So this one we can write 2 into u bracket start v minus small u divided by, this is vq. This is our equation number 3. This is our equation number 2. So three things we have identified. One is force, next work done, next efficiency. Now this equation will be give you the efficiency of the wheel. Efficiency of the wheel. Okay. And for the given jet of velocity, when the efficiency will be maximum, that means we can find out the maximum efficiency. This one, efficiency maximum. So how to find out this maximum efficiency? So for this we need to do some kind of derivatives. Okay. So first of all we need to consider, I'll write this one later. First let me tell you how to find out this one. So we'll do derivative of this efficiency term with respect to the du. Okay. So that is equal to 0. We need to consider the efficiency will be maximum when this will be 0. Now, so what is the term is there? D, if you consider, this is the condition is there when this one will be 0. Now we can write this is du by d, and this is 2 into u v minus u. This way we can get bracket with respect to, this is v square. This is equal to 0. Derivative of this 0. So now we can do one thing. Derivative of this term equal to 0. Now what I'll do, just derivative of these things. So what I'll get here, 2 into 2uv. This is v actually. This is v. This is u. Now 2uv. So du by du will be gone. So remaining will be 2v, and this is minus. So it will be, next one is 2u square. 2u square. U into u. 2u square. Derivative of that will get 2 into 2u divided by v square will be there in the denominator. So this is equal to 0. Now just to solve it, we'll get 2v minus 4u equal to 0. Now what about the velocity v? velocity v, we can write 4u divided by 2. So that means 2u. Now see, this is the equation what we got. So again we can write this one, v equal to, or you can write u equal to v by 2, or 0.5 v we can write. Okay, so this u equal to what? The when velocity, v equal to what? Z velocity. So it should be half of this. This one should be half of this. So now you can write, this is efficiency. When we will get the maximum efficiency? When we can get 50%. That means, let me write the maximum velocity equal to, this is 2u already there in the equation, if you see 2u, and here in bracket, in place of v, let me put the value of 2u. So 2u minus u divided by denominator, how much is there? V plus, I can write 2u, so 2u square. That means 2u into 2u. Okay, and here if you get, this is 2u into 2u into u, so that means 2u square, and here this is 2u into 2u. So here 1 2u will be cancelled. So what will get? This is u will be cancelled here, u will be cancelled. So we'll get 1 by 2, or that is nothing but 0.5, or you can write this is 50%. So what is the condition for maximum efficiency? And we'll get maximum efficiency this much, 50%. And the condition of efficiency is this one, maximum efficiency is this one. So I hope you understand this derivation. It is very, very simple, not that much difficult. Only we need to consider few phenomena we need to consider. One is like mass flow rate. When you consider, that time we need to consider only rho AV. But when you consider jet strikes the vanes, okay, in that time we need to consider the relative velocity. As I told you, because both are moving, the plate also moving, jet also moving. Okay, when two things are moving, we need to consider the relative velocity in that. I hope you understand. Still, if you are having doubt in this, you can give a comment on the comment box. Thank you all.